Okay, our next speaker is Simon Scannell. Seems to be very popular. Okay. There you go. This is Simon.
Okay. So, hello everyone. Welcome to my talk about a common bypass pattern to exploit modern web apps. Who am I? Let's just get us off the way. My name is Simon. Actually, I think I'm going to move this thing here. Let's get us off the way. My name is Simon. I'm a vulnerability researcher for SonarSource. I discover and disclose 0 days recently in WordPress, Magento 2, the Linux kernel, Counter-Strike Global Offensive, and I like to travel. That's why I'm really happy to be out here in Budapest, meet everyone in person, give this talk here. And yeah, we're going to be talking about some of our recent work, which includes WordPress. We discovered a CSRF to remote code execution chain. This happened in 2019. This was before browsers actually implemented same-site cookies by default, which means we had an entire remote code execution that worked on default settings, just all the way through. You would send an administrator a link, they would click on it, and then you would have a shell on a targeted WordPress instance. Then we had a remote code execution chain in Magento 2, where we utilized a pre-auth stored XSS into the admin panel. And the next time an administrator actually logged in, viewed an order cancellation, they would trigger a malicious XSS payload. And then we would chain this with another RCE exploit just to gain full control of the underlying server. Then we have a similar chain in MyBB, that's popular forum software, where we compromise the private messaging component of the software, where you could send an administrator a private message or a moderator, let them know something, and then a hidden XSS payload would run as well, which would execute an RCE exploit and then gain full control of the forum. And then finally, we would have the Zimbra webmail compromise via email. Zimbra, it's an enterprise level webmailer, where we found multiple exploits where you could send any user of an organization an email, and when they viewed it, an XSS payload would trigger again and would be chained with another vulnerability to gain full control of the underlying infrastructure. So these are all open source applications, and they've been hardened for years through years of bug bounty programs. In the case of Magento 2, they've paid out multiple millions of dollars for RCE exploits. There's competition in the zero-day market, let's say for WordPress or MyBB. They're listed by popular zero-day acquisition programs such as Zerodium. We've had plenty of static analyzers thrown at them. We've had tons of different tools to find bugs, and we've had independent security audits. But these bugs still occur, and the question is, why does this happen, and how can we find bugs in there? So over the last current years, we've noticed that the way web security bugs are found is changing. It's just become clear in the IT industry that fixing isolated security bugs in software doesn't really change anything. It's like sometimes we introduce a new vulnerability with a commit that's supposed to fix another. So vulnerabilities keep arising, and it doesn't really have any realistic impact to just kill singular bugs. Instead, we try to kill entire bug classes. We see this with mitigations. We see new frameworks coming up, which try to have a secure by default framework where you don't have to explicitly sanitize something. We have new sanitization libraries that work. And then we have ensuring overall security checks, which greatly improved security as well globally. So whenever a new mitigation or like a new fancy sanitization framework comes out, we have to look for bugs in places that are not covered by this new mitigation. This forces us to improve offensive security research and invent new ways to find vulnerabilities, which is what we have seen in the recent years in web, where we've seen bugs increasingly exploited due to parser differentials. We've had Orange Tsai give an amazing talk on this, where he detailed how to find parser differentials whenever there's like an undefined aspect of a spec, such as the HTML spec, or when there's implementation details, differences, you can find vulnerabilities in there. And then we've had different ways, such as time of check, time of use, which is just another way to gain the same vulnerability impact that we've always had, like such as XSS, injection attacks, deserialization attacks, whatever it is. But we just have a different way of getting to those vulnerabilities just because the overall security checks have improved. And what we're going to be talking about today is something similar, something that we've noticed over the years, which we feel hasn't been getting enough attention, which is modification of sanitized data. And what this means is, we'll go into detail about this in the next slides. This is what the rest of the talk will be about. Yeah, so let's build a model for finding bugs. Why would we want this? So we have a generic hacker code lead picture here, and it represents just how complex the code base can be when you're not familiar with it. Say you have a 1 week time frame for auditing a huge project with millions of lines of code, and you have no idea how the code works, how any of it fits together, and you're just trying to make sense of it. And a way to do this would be to reduce the complexity by actually knowing what you're looking for in common patterns. So let's just go really easy here and start with a very simple example of pseudocode, what usually happens in a secure web application. So you'd have some kind of user input, whether that's a get parameter, a post parameter, whether that's a JSON input, whether that's a file that's being uploaded, whatever it is, you would have user input that does something, and then you would sanitize it, and then you would use it in some way. We'll go into detail what some examples of that would be. But normally stuff isn't that easy. So sometimes when you have user input, you would transform it, you would normalize it, you would sanitize it, and then you would use it. So there's a lot of stuff happening with the data. It's actually being processed. And let's talk about what transformation would be, for example. So examples of this would be converting shortcodes to HTML. So I listed MyBB as one of the softwares that we found a bug in earlier, where you had a forum, and typically you have something like shortcodes, where you can convert the shortcodes to HTML. So you would transform the user input. Sometimes you want to modify an HTML attribute or add them to an HTML string that was generated out of the user input. Maybe you want to modify a generated template, whatever, because you have certain restrictions. Sometimes you want to censor text, say you're in a context where you're implementing a chat application. Sometimes you want to make URLs clickable, so you would have a way to detect URLs in a user input stream and then convert them to A tags, to anchor tags. Sometimes you want to translate entire inputs of a user. And that would be examples of transformation. Then we would have another step, which would be called normalization. This is what we categorize things as Unicode normalization, path normalization, length truncations, if you want to make sure that all your inputs only have a maximum length. You would ensure that all the URLs have been decoded, correctly encoded in whatever context you want to use it. All of this is obviously just without any overarching context, just to give you an idea as to what these things mean. And then finally, you have sanitization. This is where you do your extension checks. This is where you do your HTML encoding to ensure you don't have XSS. Then you have something like escaping your inputs for SQL queries, so you can use them safely without your whole application blowing up. And then you have something like validating input against an allow list. Say if you want to read a file from a server and you want to have the user specify which file, you'd have an allow list. Now, what could possibly go wrong? Because things always go wrong in IT security. That's why we're here. And what I want you to notice here is that we have the same steps: sanitization, normalization, and transformation, and then usage, of course, but they're in a different order. So in this case, we have the sanitize function first, which acts on the user input, and then it does whatever it does on it, depending on the context of what kind of application we're actually executing. And then we have the normalization function, and we transform the input afterwards as well, and then we use the data. Now, this is not secure, or it could not be secure, because when we modify sanitized data, the effects of the sanitization could be negated. And what exactly this means, we'll go into more details and examples and case studies into this later. But for now, all you need to know is that sanitization should always be the very last step. It can be easy for developers to kind of trust sanitized data because they feel, okay, I've done my duty, I've added the HTML encoder the annoying security person wanted me to add, and now I can just carry on with all my transformations and whatever I want to do with this input. And sometimes this happens by accident or unknowingly. Say if the sanitization and normalization steps are just millions of lines of code apart, or they even located in different repositories. So for example, if you have a developer working on whatever piece of input they receive from the user, and then they supply it to their database driver, and the database driver is maintained by an entirely different developer, and then that developer all of a sudden truncates the input to a certain length, or they make sure that it's in a certain Unicode encoding. So sometimes it's not very obvious when this happens and can be millions of lines apart. So let's dig into some case studies to see how this would actually play out in a real life scenario. As the first example, we have Zimbra Webmail. We've mentioned earlier, it's an enterprise-ready webmail solution. What that means is basically you install a new server, you get a mail server, you get an IMAP server, an SMTP server, you get a web interface to read your emails. According to their website, it's used by over 200,000 businesses, government, and financial institutions, which makes it quite an attractive target. And email bodies can contain arbitrary HTML code and must be carefully sanitized by a webmail solution. Obviously, this makes it pretty interesting because there's a lot that can go wrong if you want to sanitize HTML, especially because emails can and must contain HTML code, such as tables and buttons and links and whatever. And you have to differentiate between valid HTML and sanitized HTML and potentially dangerous HTML. So we discovered an XSS vulnerability, as a spoiler here, and an SSF vulnerability that allowed stealing cloud provider credentials, for example, from AWS, Google Cloud. And one email is enough to potentially take over an email server of an organization. We have a demo here before we dive into the technical details. So what we're looking at here is an attacker dashboard that's very fancy. And they're entering the email address of a targeted user they want to own. They launch an attack. And now this employee is logging into their Zimbra instance. They're logging in. They received an innocent-looking email. They're being distracted by a cute puppy. Nothing's happening. And now we've switched back to the attacker. And the attacker is now going to reload the page. And all of a sudden, they have access to all emails of the user they targeted. For example, in here, they have access to the super secure secret password for the production environment. And if you look closely, they also had access to the AWS IAM key just by chaining two bugs. The first was an XSS bug that occurred when the user viewed the email, and then they chained it with the SSRF. So that was the first demo here. So let's get into some details. How did it work? Whenever an email was received by the Zimbra server, they essentially did a server-side sanitization of the email body. They used an allow list of HTML tags and elements, which is the way to go, in my opinion. Everything else just doesn't work. They used the OWASP Java HTML sanitizer. OWASP is known for the security interests, and it was close enough to the HTML specification. And we personally did not discover a bypass in this HTML sanitizer framework. Doesn't mean there isn't one, just that we didn't find one. In this case, we were like, okay, what can we do? We also faced another problem, which was that they were rather strict in what they allowed and what they didn't allow. So what you're looking at right here is all the characters they were HTML encoding. For example, they used to encode the ampersands, single quotes, double quotes, whatever it was, just to make sure that no input could be in any way dangerous. So we decided, okay, we can't bypass the actual sanitization framework. So what should we do next? We had to look for some place where the sanitized HTML was modified before being displayed to the user. And we found a code snippet in a JavaScript file located in an entirely different repository. And this just highlights that these steps where something is being sanitized and where something's being actually used before, or where something's actually being transformed before it's being used, they can be in an entirely different context, meaning one can be on the server side, one can be on the client side. So we use modification of sanitized data to secure an XSS. So an email can contain calendar invites. Most of you have already probably used them. Whenever you become a link to a Google Hangout or whatever, or a Zoom meeting, they'll let you know in the email when the meeting is going to happen. And it's just part of the email specification, how this works internally. And basically, if such an invite was present, the front-end JavaScript file was used to truncate the HTML description of the invite. So this is the actual code, the actual vulnerable code. We checked if there's a calendar invite, and if so, there were some other checks that aren't interesting. And then we would actually enter the truncate body content function or method, where content contains the actual raw HTML string that has been sanitized. So this is user control input, which has already been sanitized. And this is code within this function. And now this is where it becomes interesting. The way they did this is they created a new div element, and then they added the content as the inner HTML attribute of that newly created div. And then they use the JavaScript API to search within the user supplied email HTML just to find an ID, which was the separator ID, which just tells the code where to truncate the rest of the content from. Basically, this is just a fancy UI trick to make sure descriptions of meetings aren't too long. All of this isn't very relevant to the code. The only thing I want you to notice is that the div element has the inner HTML attribute set to the content. And now what this does is it decodes any HTML encoded entities that don't strictly need to be. So this is kind of a normalization step, just because browsers normalize the input so that all the input is the same as expected. And the browser in this context wouldn't expect HTML attribute values to be encoded in any way. So they just decode this entity. Now, this does not lead to XSS directly, but it's important for the next step, and we'll show actual code snippets on what to expect and what this means. So the JavaScript front-end lookend, the same JavaScript code would then look for form tags without an action attribute. So emails can contain form tags, and if no action attribute is set, the action attribute dictates where the request of a form should go. And if it isn't set, the request goes to the same page. So technically speaking, you could send someone an email with a form without an action attribute, and if it isn't present, you can forward a request to the same page as the user is currently viewing, and it's kind of a CSRF attack. Probably not very critical in most cases, but it's a good thing they changed it. So what they would do is that JavaScript code would look for this form tag and then add a default action attribute. And if this code looks scary, we'll just see in a minute what this does in action. But basically what it does, it looks for form tags without an action attribute. We have a negative look ahead in the regex. And if it does find it, it just replaces the entire thing with a default action attribute that says same host form post blocked. I actually never know how to say this correctly. And it just inserts this with some double quotes. So let's just assume the following HTML in an email. Say we send an HR attribute, which is just a line break, which is totally valid in the HTML spec, and this doesn't get sanitized away in any way. So as you can see, the align tag contains a form attribute, which is valid because it's enclosed in double quotes. There's nothing wrong here. And then the no shade attribute contains a script tag, which is also enclosed in double quotes. So it doesn't actually do anything, which is totally secure. So after the server-side sanitization, these tags become escape nonetheless, just to make extra sure, which is the way to go. But then after the normalization step, when we set the content to inner HTML, these things become decoded back again, and we have our text back, which still doesn't actually do anything for us, but we're one step further ahead. We did something the developer didn't intend to do. So after the last step, the regex replacement, we actually trick the JavaScript file to insert the form tag with the default action attribute into the string. And with it, we inject like another double quote. And now the balance of the double quotes is messed up, which leads the browser to interpret the script tag as an actual tag, which means we have just gained XSS, which is how this would work. So just to summarize, the form tags with the align attribute was matched. And then we have the insertion of the double quotes corrupts the HTML string. And then in Google Chrome, this leads to XSS. And just to like break this down again into the actual model for vulnerabilities that we created earlier during the talk is that in the beginning, we have the user input, which correlates to the email that we received. It's being sanitized on the server with an allow list, which is secure. But then afterwards, it's actually being normalized by the browser through the inner HTML spec, whatever it is. And then we have the transformation where the form tags globally on a string are just replaced, which corrupts the entire thing. And then we display the email to users, which leads to XSS. So for another case study, we have WordPress, which is at the time of writing, it's used by over 42% of websites, I pulled this data from the official WordPress site. So I guess I don't know where they have that data from, but that's quite a lot of websites. So interesting, it's an interesting target. Zerodium has also recently increased their payout for vulnerabilities for 0 days in WordPress to a couple more $100,000. So it's definitely an interesting target. And we looked at unauthenticated attack surface. And since WordPress at the very core is just a blog, they had a comment form where you could just submit any comments, say, hey, I really liked your article, whatever, yada, yada. And then the interesting thing is that this comment form can actually contain HTML. and then they do the same thing again, where they make sure that only allowed HTML and only allowed attributes are used. And we thought, okay, maybe we can bypass this. And we discovered a chain of vulnerabilities leading to RC impact in default settings. And at the time when the vulnerability was found, same-site cookies weren't enforced by default by the browser, meaning this would just work. And the comment form, interestingly enough, is not protected by a nonce. And it can contain raw HTML code, as just mentioned. And what's extra interesting is that the sanitization rules relaxed for admins, meaning you can use a lot more HTML codes and attributes that you normally should be able to. But via CSRF, you can then just create a comment that can contain a form or a table or whatever. But this isn't dangerous by itself. So we looked at the sanitizer and looked for places if there's some way that we could bypass this talk. And we noticed that the sanitizer has been hardened over the years just because everyone's been hammering it and everyone's tried to find a bypass in it. It uses an allow list, one for admins, one for unauthenticated users. And again, we did not discover a bypass for the sanitizer. So we were like, okay, what can we do? And we looked for places where comments are modified after sanitization step. So normally when you in WordPress submit a comment, it's being submitted and then it's being sanitized. And then there's a couple of filters acting on it where you could use plugins, WordPress plugins to modify the comment. Then it's saved in a database. And finally, when someone views it, it's just being displayed without being sanitized again. So comments can't contain A tags because they wanted us to just link URLs in comments. They wanted users to be able, just because it's super useful if you can just paste a comment and it becomes clickable instantly. So for SEO purposes, search engine optimization purposes, WordPress modified the rel attribute. It just basically tells the search engine how to handle this link. It's just making sure your A tags are friendly for search engines such as Google. And only administrator could set this rel attribute in links, and that's why the CSRF interaction was needed. So we would create a comment via CSRF with this rel attribute, and why becomes relevant in just a second. So WordPress would parse the A tag of the already sanitized comment and then create it. So after a comment's been sanitized, WordPress looks for this rel attribute. And the way it does this, it creates a key value pair of all the HTML attributes and values. And then it goes through those values, modifies them, does whatever it wants to do with them, and then puts the string back together. So we're looking at the actual code here, where it would check if attributes is the attribute array, if it contains the rel attribute. Now, the processing of the rel attribute is not actually relevant to what we're trying to do here, which is pawn the whole thing. So we just cut it out of the code snippet. The only thing we're looking at is this for each loop, where the actual string is being put back together, where text represents the attribute string. And as we can see, you have the name, which correlates to the attribute name, and value to the attribute value. And it's being put together, and it's being wrapped with double quotes, which is normally how you would want your attribute values. Now, what's really interesting about this is that they use double quotes without ever actually encoding the attribute value again. And in this case, let's assume an input where a title attribute, which any user can just use in their A tags, contains XSS, and then it contains a double quote, and then it uses the onmost over equals evil code. Evil code just represents your payload, and it has an ID equals and another double quote. And this entire thing is wrapped in single quotes. This is pretty important to notice just for the following steps. So after WordPress puts the string back together, obviously they use double quotes, and then the whole thing becomes corrupted again just because they didn't sanitize it again. And as you can see, the title attribute would end where the previous double quote began, and the almost over event handler is being injected. And you could inject another style attribute, make the link or span over the entire page be invisible, and when the user would move the mouse, the JavaScript code would trigger. So this is how this XSS worked. And just to summarize again, we have the sanitization step. At the very beginning, when you submitted the comment, you would send in your comment. It would be sanitized with an allow list, be secure. Then they would transform the whole thing, which means they would process the rel attribute. And well, they didn't sanitize it afterwards again, which means it's vulnerable to this common pattern where they just use the data, display the comment, and you gain XSS. We've also prepared a little demo for this. This one is a little more abstract, just because there's some details that we couldn't talk about. So we have the admin logging into their web page. So in WordPress, this is interesting to know as a fact. In WordPress, per default settings, anyone can submit a comment to a blog post, but the admin or any editor has to actually approve the comment. So they go into their admin dashboard, they see the comment, and they see a message that we use the content in their own blog post. They visit the attacker page, and then the cserf payload is used to create a XSS payload. And then because we're already on the attacker page, we just load the comment in a hidden iframe to trigger the XSS. And then we upload a plugin from within the admin dashboard using the JavaScript code. And then we got the code execution. And we took over a full WordPress instance just by having the admin click on a link. So finally, last but not least, we have a very short case study of Magento 2. It's a popular online e-commerce solution, and all the Magento 2 stores in the world, they handle hundreds of billions of dollars in annual transactions. Again, I pulled the website from the actual vendor page. This is where they got the data from. And it's popular for target. It's a popular target for hacking groups motivated by financial gain, which makes a lot of sense looking at the number of money that's being transacted. And especially hacking groups such as MageCard, they've been observed to actually use 0 days, especially with a focus on the plugins, to hack into Magento 2 stores and steal credit cards of customers and manipulate the flow of money. So low privileged employees could create an XML sitemap files. They're just being used by search engines again. And the file names, they had to end with the .xml extension just to make sure they're sane and they work. And the file name and content would be stored in a database. So when you were, say, a marketing manager of an online store and you wanted to make sure your SEO was working correctly, what you would do is you would just create a new sitemap file. You'd say, okay, I want the sitemap file to be called the following way. And then they would store the actual file name and the content in the database. And then whenever you wanted to just update the sitemap, it would be written to file, and a search engine could essentially use it. Now, the file name check was secure. You could only create file names with the .xml extension. But on an entirely different software project, which was the MySQL project, the database column for the file name was limited to 32 characters, which means the database driver class used by Magento would actually truncate the file name to 32 characters. Now, this was pretty interesting because we could create a file name with 36 characters with AAA just to fill up, just create some padding, create a .php.xml extension, which would pass the XML extension check just because it's an XML. It's pretty straightforward how to perform this check. And then it would finally be truncated. So the XML file extension would be cut away from the file name. And then we have an RCE via file write, which was kind of easy to get. Just to summarize again, we have the sanitization where we have the enforced XML extension, just showing you don't actually have to encode anything for sanitization. In this case, it was a validation. And then you would truncate to 32 characters, just normalize the data, and then write the sitemap to disk, which would be the usage case in this case. Now, in this case, we prepared a particularly fancy demo in Magento, just because we didn't have the time to just pull all of this into the talk. We also discovered a XSS vulnerability that any unauthenticated user could trigger, which would be stored in the admin dashboard. So what would happen in this attack was that an unauthenticated attacker would store this malicious XSS payload in the admin dashboard, and then they would just wait for the admin to log in, and then they would exploit this vulnerability, this XML file write, to gain full control of the Magento 2 instance. So now we're just waiting for the administrator to trigger the payload, waiting for them to visit the admin dashboard. And after this happens, we have a shell. There we go. So that was that part and the last demo. So moving on. So in summary, we want to abstract how we find vulnerabilities and abstracting how vulnerabilities work. It helps us find bugs in highly complex and large code bases, especially when we don't have enough time to just look at the whole thing. We want to know what do we look at, and we want to have a kind of a pattern, kind of a roadmap on how to use it, which helps us abstract the whole thing in the big picture way, regardless of the language that's being used, regardless of if this is a server-side bug, if it's a client-side target that we're looking at. That's kind of why we want to do this whole abstraction thing, just to help us find the bugs. And we just look for places where sanitized data is modified, just because a lot of times it's much easier than actually finding a bypass for the sanitization step. And for developers, sanitization must always be the last step. If there's no other way, maybe just sanitize twice just to make sure, just to ensure that nothing is actually being modified in a bad way. So thank you for listening. And then I guess it's time for questions.